Hi, and welcome to another physical science lesson. I am your presenter, Nico Swartz. Today we'll be looking at electricity. If we think about it, there's always that one chapter that we love, and then there's a chapter that we do not love. And unfortunately, in my experience, I've picked up that this is one of the chapters that's poorly answered. So let's try and see if we can get through all of the struggles and get a clear understanding of what is required to answer any questions related to electric circuits. Let's go and have a closer look at what we need to know in this particular chapter. Join me on the board. Come on. We will be looking at Ohm's law. We'll also be discussing the difference between series and parallel circuits. And there's a lot of theory that we need to talk about to get a better understanding of the calculations. We will then also talk about power and a quick discussion on the cost of electricity. Ohm's law. We need to have a closer look at what Ohm's law is trying to tell us. Now, at a glance, it simply looks at the relationship between potential difference and current. And it is the case with many of other investigations. Other variables need to be kept constant when you investigate two variables. Join me on the board and let's have a closer look at what the law states. Because remember, you need to be able to rewrite this law if it is asked. So we need to go and memorize the law, but with memorizing, we need to also understand what the law is saying. Join me on the board. Ohm's law states that the potential difference across a conductor is directly proportional to the current at a constant temperature. In a mathematical form, we've got that the resistance is then equal to the potential difference divided by the current. What does all of this mean? On a graph where we've got the potential difference in volts on the y-axis, and we've got the current in ampere on the x-axis. This is what we'll see, direct proportionality, V directly proportional to current. What that means is, if my potential difference increases, it would result in an increase in the current. So when we represent this graphically, this is exactly what we will see. The yellow line representing a positive direct proportionality. The question comes in, what does the gradient of this graph represent? Now we know that gradient is defined as the change in y over the change in x. Gradient therefore represents the resistance. Again, the gradient of a potential difference versus current graph represents the resistance. Ohm's law, in a nutshell, simply says that the potential difference is directly proportional to the current, provided that the resistance, or sometimes we also say that the temperature of the resistor remains constant. Why do we say temperature again? That is because temperature is one of the factors which would influence the resistance of a resistor. Let's continue. Join me on the board. Non-ohmic conductors. Now, by just understanding what this means, we'll understand what the graph represents. So non-ohmic meaning it does not obey Ohm's law. Let's have a closer look at the graph. We've still got potential difference on the y-axis, and we've still got the current in ampere on the x-axis. But if we go and have a closer look at what's happening with this graph, so this first section, it is still a straight line graph, meaning at that point, it still obeys Ohm's law. But when we look at the next section, from there to there, we start seeing a curve. And the gradient seems to be steepening. It's becoming steeper. And in fact, for this third section, you will see that the gradient there is much bigger. So let's put there gradient. For that particular section, we will see that that gradient is steep. So there, remember the gradient of the graph represents our resistance. So for that section, the resistance will be very high. And it's very high compared to the section that we've got here, section 2, and then of course, we've got section 1 over there. So in actual fact, a non-ohmic conductor initially behaves like an ohmic conductor. But something happens at these 2 points that causes the resistance to increase. And that is what makes it a non-ohmic conductor. Let's, for a few seconds, go and see whether you understand Ohm's law. And we do this in a simple multiple choice question. Join me on the board and let's analyze what the question wants us to determine. Learners investigate the relationship between current and potential difference. And this is done at a constant temperature. Why do we want constant temperature? Remember, temperature influences the resistance of a resistor. So we've got 3 resistors, X, Y, and Z. And the following graph is obtained. And if we investigate, we'll see X, Y, Z are at different gradients. They are all straight line graphs, which means they are all ohmic conductors. Good. All of them are ohmic conductors. What is the question asking of us? Which one of the following conclusions regarding the resistance of the resistors is correct? So we want the one which is correct. Now you'll agree with me that multiple choice questions can sometimes be a bit of a headache. And I like to use a little bit of a strategy when you approach these questions. And the first thing I tend to do is not look at the options. Don't look at what A, B, C, and D is showing you. Try and determine the answer to the question before looking at your options. And then the other strategy is to use a process of elimination. So those answers that you know will definitely be incorrect. You eliminate them until you are left with one answer. And if that answer corresponds to what you determined previously, then it should be the correct answer. Let's go and have a look at how we can address this particular problem. Alright, so we need to look at the relationship between the resistance of the resistors. Now here's our graph in miniature form. Now mathematically, what do we see? We see that the gradient of X is much bigger than the gradient of Y, and Y is bigger than Z. So we'll tend to say that the resistance of y, or of x rather, the resistance of x is bigger than y, and y is bigger than z. But here's a small little problem. What is gradient again? Let's write it over here. Gradient is equal to the change in y over the change in x. What is on the y-axis? Current. What is on the x-axis? Potential difference. And resistance is equal to V over I, and not I over V. So in actual fact, what this gradient represents is 1 over R. The gradient represents 1 over R. So now we know. Let's quickly write it down for ourselves. We're looking at the reciprocal values. So therefore, it means X will be smaller than Y, and Y will be smaller than Z. There we've got our answer. All we need to go and do is look for what we've determined. All right, process of elimination. B, they are not equal to each other, so B is out. Then, what is the next obvious one? So the resistance, if we look at what we wrote down over here, which one is the biggest? The biggest is Z. So if we had to rewrite this in another form, Z is bigger than Y, and Y is bigger than X. We just need to go and look for one of these two options, and we will be fine. So what we see in A is that Z is bigger than Y, and Y is bigger than X. This seems to be correct. Let's look at all the other options. C says that X is bigger than Y. That's not what we've got here. X is smaller than Y. So process of elimination, let's take that one out. What does D say? X is bigger than Y. This is also out. That leaves us with an obvious answer, which must be A. I hope that this demonstration shows the approach to any of your multiple choice questions. What did I do? First, look at what the answer possibly is, without looking at the options given. Then, by the process of elimination, take out all those answers which are incorrect. And when your answer you determined without the options corresponds with your elimination process, you will have your correct answer. At this junction, I'd like to say, let's take a break. Let's go have a drink of water. We come back refreshed, and we tackle more of this electric circuit questions. Welcome back, guys. I hope you are rested and ready to tackle a little bit more on electric circuits. Let's go and have a closer look at what is meant by series and what is meant by parallel. Because I find there's a lot of misconception around series and parallel. And some of the definitions you hear is series is when they are behind each other. That's now resistors or cells. Or you hear parallel is when they are next to each other. But behind each other, next to each other, those are very relative terms and very unclear. Let's go and have a look at a better way to identify what is parallel and series, and a little bit about what is the theory that we need to know regarding those two types of connections. Join me on the board. So, series and parallel. Now, a series circuit only has one path. This is very important for the charge to flow through it. Opposed to parallel or branched circuit that has more than one path. Quickly, if we draw that quickly, if we've got two resistors in that type of orientation, there's only one way in which the current would flow. It only has one option. Therefore, that is series. If I've got my two resistors connected in this fashion, with the current flowing again from the left side of the screen to the right side, then you'll see the moment the current reaches this point, it's got an option. I can either go up or I can go down. And that is referred to as parallel. Parallel. So we understand now what is the difference between series and parallel. What is the theory we need to understand? Let's just focus on one. Let's look at series. Remember, there's only one pathway that the current can flow. It's very important to remember that potential difference is divided in proportion to the resistance. So if potential difference is divided for each of my resistors, it means I can go and calculate the total potential difference as potential difference 1 plus 2 plus the potential difference of the third resistor. And then this is also important. The current remains constant in a series circuit. Let's have a look at parallel connections. Remember, this is where you've got branches and the current has an option to take pathway number 1, 2, or 3, or even more. Important to remember is that the potential difference is always constant. So if you've got the potential difference of one resistor in parallel, you'll have the potential difference of all the resistors in parallel. That means V total is equal to V1, which will also be equal to V2, which will also be equal to V3. Current divides in inverse proportion to the resistance. So in parallel, each branch will have its own current. But if you add those currents together, you'll find your total current. Let's summarize quickly. In series, we need to talk about the resistance. And what we should notice is that the total resistance in series is calculated as the sum of all the resistance of the resistors. Opposed to in parallel, we need to go and calculate the equivalent resistance. And we've got two options here. The first option is we use a little shortcut, but this is very important. When there's only two branches, only two resistors, then we can use that the equivalent resistance is equal to R1 times R2 divided by R1 plus R2. All right. But remember, that's only when the resistors are 2. When there's more than 2, we need to go and use the very long formula that we can see over there. And we need to go and look for the lowest common denominator. Don't forget, to get R equivalent, we need to take it to the top. We need to invert in our calculation. So in summary, if we've got a series circuit, potential difference of the different resistors will be divided. That means if we add all of them together, we should get the potential difference across the battery. Also with series, the current remains constant. Whether you take the current after resistor 1 or after resistor 3, the current will remain constant. If we look at parallel connections, we see that the current is divided. That means each branch in your parallel connection will have its own current. But if you add those different currents, it should give you your total current. Also, if you've got the potential difference in any of those parallel resistors, that would be the potential difference for all the resistors. Now that's a lot of information to take in. I think it becomes clearer when we start looking at problems. So let's go and look at a specific problem and try to answer the questions. Join me on the board. Our question shows us that we've got a potential difference across the battery of 6 volts. Here, if the current is flowing in this direction, we'll see it branches and it's got 2 resistors, a 4 ohm and a 6 ohm. And they give us the current flowing in the 6 ohm resistor branch. There is V1, and if we have a close look, you'll see that V1 is measuring the potential difference across the parallel combination. So we can also refer to it as V parallel. The current continues and passes through an unknown resistor X, and V2 is taking the potential difference across resistor X, and our current continues through our closed circuit, and there in series we find our ammeter. So let's quickly just talk about strategies that I like to use. The first thing is you must always try to find what is the total current of the circuit. I believe if you've got the current of the circuit, you can literally calculate anything. Then the second thing that I like to do with these questions is that I don't look at what the questions are. I immediately go and try and answer as much as I can. And more often than not, I find that when I look at the questions, I have actually answered them before I've even seen them. So let's see if that is applicable. So we're taking the question and then we're going to answer without knowing what the questions actually were. Join me on the board. So let's skip the questions. We don't want to know those questions. And so the question shows, but that's not what we're going to look at. Let's just analyze what's happening. Where is my starting point for this particular question? That is usually where you find the most information. And this for me is an obvious point of interest because there I've got a current and I've got a resistance, which means I can go and calculate potential difference. All right? So our basic formula that we use for everything is V is equal to I times R. Now I like to include subscripts because it gives me a better idea of what I'm calculating. And our theory says this is a parallel connection. And what do we know about potential difference in parallel? We know that potential difference remains constant. That means if I calculate potential difference of the 6 ohm as I'm about to do, I would know what is the potential difference of the 4 ohm, and therefore I'll actually be calculating what is V1, which is V parallel. All right, so if we substitute now, it will be the current, which is 0,6, and the resistor, which is the 6 ohm. That's why you see my subscript indicates a 6 over there. That is equal to 3,6, and we've got volts. So we've actually gone and calculated what is the reading on V1. Now, what is the next thing we can go and calculate? Knowing what V1 is, we can go and calculate what is the current flowing in the 4 ohm. So we can go and say the current in the 4 ohm is equal to V over R. What is the potential difference at that 4 ohm? It's in the parallel combination, therefore I will have V parallel there. We are looking specifically at resistor 4 ohm. So let's go and substitute. V parallel is 3,6. And the resistance that we are looking at is the 4 ohm. And 3,6 divided by 4 gives me 0,9 ampere. This is another important milestone in the calculations, because we know that current is divided in parallel. And if current is divided in parallel, it means the current in the 4 ohm plus the current in the 6 ohm should give me I total. What was our main goal? Was to find I total. Once you've got I total, you will be able to calculate anything. So that is, I total is I in the 4 ohm plus the current in the 6 ohm. And that gives me 0,9 plus 0,6. And that gives me a final answer of 1,5 ampere. We've got the total current. Let's quickly go and see what else we can calculate. We can now, because we've got the V parallel, which we saw was 3,6 volts, we can go and calculate V2. V2, which is in series, is the total, V total, minus V parallel. And that gives me 6 minus 3,6. Now we know that V2 is equal to 2,4 volts. Very important. Now that we've got the voltage here, we know what the total current is that's flowing. 1,5 ampere. We know what that total current is. We can go and determine what is the resistance at X. So resistance is equal to V over I. We are specifically looking at resistor X, and we just determined that the voltage there is 2,4, and we know that the current is 1,5. So that gives us an answer of 1,6, and that is ohm. So we've got just about everything sorted. Let's quickly go and have a look at how you can actually test these answers that I've just calculated. Isn't that nice? You go and calculate. You can go and test using different methods. You can test whether your first answer was correct. In actual fact, you can walk away from a paper and already know whether or not you've got full marks for that particular question. Let's go and have a look at how to do that. Okay, Anele, so this, I'm really... 3, 2, 1. Calculate, so the current passing through the 4 ohm resistor. We want to know what I is at this particular point. And you will agree with me, we've actually gone and calculated that already. But let's go and have a look at how a different approach would have worked. So we could go and calculate what is the potential difference for the 6 ohm. Potential difference at the 6 ohm is equal to I times R, and that is R6 because it's for the 6 ohm. The current flowing there is 0,6 and the resistor is 6. Therefore, we get the 3,6 volts. And our theory says that is the voltage also at the 4 ohm. So, therefore, the current at the 4 ohm will be equal to V over R. We substitute 3,6 because potential difference remains constant in parallel, divided by the R we're looking at. The R that we're looking at is the 4, and therefore that is equal to 0,9 ampere. All right, so that is answering question 2.1.1. Calculating the current through the 4 ohm resistor. Let's have a look at what question 2 asked. Calculate the total current passing through the cell. So total current, we know current is divided in parallel. Therefore, we've got the current at the 4 plus the current at the 6. The 4 is 0,9 ampere, and at the 6 we've got 0,6, and that gives me the total current of 1,5 ampere. Once again, we have answered this particular question in the previous explanation. 2.1.3. Calculate the resistance of X. Now, this is where I'm going to use a different method to the first explanation. We can start off because we know what is the potential differences. We can use that to calculate X. What do I mean? Let's have a look quickly. We know that the V total is equal to I total times R total. So V total is 6. And the current, the total current is 1,5. What is my R total? We haven't worked that out because, remember, we don't know what is X. Now, R total is therefore equal to 6 divided by 1,5, which gives me 4 ohm. So now I've got the total resistance, and we know that R total is equal to R parallel plus R in series. Now in parallel, we worked out. Did we go and work out what is the parallel resistor's equivalent resistance? No, we haven't, but we can quickly do it. It's 2 resistors. So it will be 6 times 4 over 6 plus 4. And all of this will be added to X. We don't know how much X is. We know that R total is equal to 4. All we need to do is to make X the subject of the formula. And once again, we'll find that X is equal to 1,6 ohm. And this is what I meant when I said you can go and test your answer. Because you've got more than one option. You can calculate with one and you can test with the other. Again, rather do that if you know you've got enough time to go and test those answers. At this junction, I think take a break and then you come back refreshed and we look at the next problem. Welcome back, guys. I hope you are well rested and ready to work on the next question. Before we actually go to the next question, there's just one interesting thing I would like to ask you, and I'm sure you've got the answer. Let's go and have a look at what am I talking about. So from the previous question, the 4 ohm resistor gets hotter than the 6 ohm. Alright, so we're looking at this 4 ohm getting hotter and faster than the 6 ohm. What is the difference between them? Yes, the resistance is different, but it's important to understand that the current is also different. Remember, the current we got here was 0.9. And what is the implication thereof? Yes, we know that resistance is actually directly proportional to the reciprocal of the current. What are we actually saying? If the resistance increases, the current will decrease. Okay, what is the implication of this? We need to go look at, because they're talking about hotter. What is that? We are referring to energy. And we know that W is equal to VQ. All right? Then what is V equal to? V is equal to I times R. What is Q equal to? Q is equal to I times T. So rearranging this formula, we've got that I squared R times T is equal to energy. So think about it carefully. Look at I squared in this equation. The current is much higher in the 4 ohm. So the higher the current, the more energy. That is, of course, if the resistance is constant and it's all done in the same period of time. Alternatively, we can look at the other formula for energy. Energy is equal to V squared divided by R multiplied by time. In this case, we're not looking at the current, but we're looking at the resistors. What is the mathematical relationship between the resistance and energy here? You can see they are inversely proportional, meaning a small resistor will yield more energy, or it will dissipate rather more energy in the same period of time. I hope this explains why that 4 ohm resistor becomes hotter much quicker than the 6 ohm. So you've got 2 options there. You can look at the resistance or you can look at the current. But it's important for you to link it to the correct formulas. Alright, let's jump into our next challenge. Are you up for a challenge? I definitely am. Let's go and have a look. So we need to talk about power. Now, what is power? Power is defined as the rate at which electrical energy is dissipated in an electric circuit. Now, anything to do with rate refers to divided by time. So power is equal to energy divided by time. Sometimes also written as power is equal to work done divided by time. Remember, work done is also energy. Power is always measured in watt, and 1 watt is equal to 1 joule per second. Alright, where does this come from? Comes from the formula. Power, which is watt, is equal to energy is measured in joules, and time is measured in seconds. If you take the seconds to the top of your division line there, it becomes J dot S exponent negative 1. So power is energy divided by time. What is the unit of power? No. That was not a question. It was a statement. What is actually the unit of power? Let's go and see this in practice. Join me on the board. Consider the circuit diagram below. We've got an EMF of 12 volts. We've got two resistors which are in parallel and an 18 ohm which is in series. Some warning lights are going off. What is this EMF thing now? This is the first time that it appears. What does EMF mean? So the abbreviation is for electromotive force. Now that tells us what the abbreviation is, but what does it mean? In actual fact, the EMF measures the potential difference across the terminals of your battery in the absence of a current flowing in the circuit. So that's a little bit contradictory to what is happening on the screen. Because at the moment, the screen shows that your current is flowing. It's a closed circuit. So in actual fact, it should have been a V external. But this is a discussion for when we've got internal resistance. This question does not have internal resistance. So the EMF is just referring to what the potential difference is across the terminals of the battery. Let's go and use what I've explained before. So without looking at what the questions are, let's see what we can calculate very quickly. Join me on the board. We can start off by looking at what is the equivalent resistance in parallel. It's only two resistors, so it will be 60 times 60 divided by 60 plus 60. And without a thought, that will be equal to 30 ohm. Another hint, guys, another hint. If you've got two identical resistors and they are in parallel, the effective resistance is always half of that one resistor. So half of 60 is 30. If you've got a 40 and a 40, half of 40 is 20. So the effective resistance of a 40 and a 40 would be 20. You get the picture? Right, let's continue. We can also go and calculate what is R total, because we've got the 30 now, which is in parallel, plus we've got an 18, which is in series. So my total resistance of my circuit is 48 ohm. Okay, good and well. We've also got the total potential difference, or the EMF, which is equal to 12 volts. We can go and calculate the total current. And you'll remember this is what I said. We need to go and find the total current. Once we've got that, it doesn't matter what the question asks of us, we'll be able to calculate it. So the total current flowing in the ammeter will be equal to V total over R total. And we've got both these values. We've got a we've got a 12. We've got a 12 over here. And that 12 divides by my total resistance of 48, and my total current is therefore equal to 1 over 4, which is a 0.25 ampere. So that is as much as I can possibly go and calculate. Obviously, if we want the current in the different branches, it will be identical current. So we can simply divide this by 2, which will give me 0.125 ampere flowing in each of these branches. That is as much as we can calculate for this particular problem. Let's go and see what was the questions. The question is asking, calculate the equivalent resistance of the parallel combination. Let's just check on the screen. We've done that. Tick. Next question. What is the reading on the ammeter? That is the total current. The total current. What did we have to do? We had to go and do this little piece and all of this to go and find what was the total current. Next question. the potential difference across the parallel resistors. V parallel is equal to I times R parallel. So the total current was 0.25 multiplied by R parallel's combination is 30. That should give us 30 divided by 4, 7.5 volts. The next question asks, we must calculate the power dissipated by the 6 ohm. Now we've got a couple of options, but the easiest one is power is equal to V times I at that particular point. So the potential difference at one of these 60s, we just calculated. The potential difference there is 7.5. And the current flowing in one of these, remember the total current was 0.25. The current flowing in each of them is identical, so we can just divide it by 2, which gives me 0.125 ampere. Therefore, the power dissipated there is 0.9375. And remember, we actually need to go and round off to 2 decimal places. So that is actually equal to a 0.9, and I would round the 3 off to a 4 watts. Very quick, very easy. There's a different way you can also go and calculate it. Different formulas you can use to calculate power. But that concludes what we have for this particular lesson. We just need to go and summarize what did we look at. Let's have a look. We discussed Ohm's law, and we said potential difference is directly proportional to current provided that the temperature of the resistance or the resistor remains the same. We had a look at series and parallel circuits. Remember, in series, current is constant, potential difference divided. In parallel, current is divided, potential difference is constant. Then we discussed power, and we said power is the rate at which energy is dissipated. Cost of electricity, this is a question that we usually do all the way from grade 8, but this is just how much electricity costs per kilowatt hour. And these are simple conversions and rates that we use, so mathematical problems. In a brief summary, that concludes our presentation on electric circuits. I hope you enjoyed it. I hope your perspective about this particular chapter has also changed and that you feel a little bit more positive. I look forward to seeing you in all the other lessons that we'll be presenting. From me, Nico Swartz, have a good day.